Okay, so as promised, this is a short video about linear regression in the general linear model. So we're talking about chapter 17 and 18. These are just the highlights. So off we go. As a reminder, we talked about linear association, how to estimate the correlation and test whether it's statistically significant. That was chapter 16. And we made a point about saying that correlation sometimes is indicative that there's an actual cause here. So for example, just to give you a sense of this, I have plotted here the parts per million of CO2 in the atmosphere measured on Mauna Loa. You should recognize Mauna Loa. Mauna Loa is currently erupting, and so that's an interesting thing. But so we're well over now 400 parts per million, whereas back in the late 50s we were down to about 320 parts per million. And along the line we can see that there's a correlation between global temperature, the difference between sort of what was typical and what we're seeing now. Right? So we do think that that's a causal relationship. The more CO2 in the atmosphere, the warmer the temperature. But there are many other associations that we don't think that there is a causal relationship. And so this is a famous graph from a repudiated report in the journal The Lancet. And it's about looking at the measles, mumps, rubella vaccine, and people had hypothesized that there was a link between getting the vaccine and autism. And so this is the actual graph that was used. And so the short answer is that many studies have come and gone basically pointing out that this is what we'd call a spurious correlation, not a causal relationship. All right, vaccines don't cause autism. All right, so chapter 17 talks about linear regression, and it has to do with linear regression of a single variable, single predictor variable, I should say. Chapter 18 is about multiple linear regression, where we take, instead of having a single predictor variable, you can have many predictor variables. And the idea is that you are developing and testing a linear model in which you're implying that x1, x2, x3, the three different predictor variables, each in turn cause the response variable to change. And the change is linear. Okay, so modeling cause and effect. Just like in ANOVA, analysis of variance, you're testing models of cause and effect. All right, so model building and machine learning, those are some things that you're going to talk about or hear talked about when you talk about causal inference. And so we're just going to put it out again here. The purpose of regression is like ANOVA. We are testing models of cause and effect, and statistics about it can be also referred to as model building. What we're trying to find out is, given one or more predictor variables, our independent variables, the things that we control from our experiments, do they cause change in the dependent or response variable? Okay, so here's one way to write them, but the idea of a simple linear regression is that we have just two coefficients that we're going to be estimating. We have the y-intercept and we have the slope. And of course, x is our predictor variable, our independent variable, and y is the response variable or the dependent variable. And then, like any model, in order to predict y's, if we know the y-intercept, the slope, and the value of x, we can predict y plus or minus some residual, some error, some leftover. Then multiple regression is just simply extending that simple model. You still have a y-intercept, the value of y when x is equal to 0, and then you can have as many estimates of slopes as you have predictor variables. Okay, so the regression equation can be kind of broken down into a couple of parts. And the parts can be talked about like the structural part, the things that allow you to make predictions. So in our simple regression, simple linear regression, we have the y-intercept and we have the slope. So those are the structural parts that predict the change in y given the change in x. And then you have the random part, what's left over, or the residual. And that is literally the difference between your observed y and your predicted y. The predicted y comes from the structural part. All right, so ordinary least squares is a particular kind of estimation procedure to test a linear association. It is a particular model or particular line that we can draw through our points, and it's the only line that you can draw that minimizes this term here, the sum of the squared residuals. So remember, we defined that as the observed y minus the predicted y. You square it, add those all up, and then each one of those points, there's a point there, you draw a line back to the green line there, and that's the predicted y, okay, and that was the observed y. All right, so this line minimizes all of those differences. No other line that you could draw will have the statistic where the minimized squared residuals will be the smallest value. Okay, so getting back up here, here's our linear regression model, how to calculate the y-intercept. Well, you set x to 0, find out what y is. Another way to do it is you get the mean of your observed y's, multiply the slope times the mean of the predictor. Okay. All right, and the regression is simply the covariance between the difference of each individual observation for x by the mean, multiplied by each observation of y, subtracted from the mean of y, and then divided by this term here. So change in x, change in y. All right. Parenthetically, we'll talk about there are certainly cases where it makes sense to not estimate the y-intercept. So theory may call for it, so a regression through the origin, or RTO we'll call it. Here's our model equation, no intercept to be estimated. So you fit the data through 0. And so the point being is that there are cases in which that would make sense to do. This isn't a particularly familiar setting for you, but there's going to be many situations in biology research where you would do your regression between two variables, having forced the regression through the origin. So phylogenetic independent contrast method, where you're doing comparisons between, say, metabolic rate and body size in multiple species, and you want to compare them to see if there's some differences that are associated with particular ways of living or something, common kind of hypothesis that you'd have in comparative biology. Okay, we all know that species are related through a phylogeny, and so that some are more closely related to each other than they are to others, and so you have to account for that in your regression model. And so this idea that the species are not independent is more generally referred to as the points show correlation with each other. So we have a method to remove that. And in the end, you're going to compare body mass and metabolic rate, and you're going to fit the regression through the origin. Okay. Some notes about this. This shows up in chapter 17, but it's also discussed in other places. But everything is the same about regression through the origin and normal regression, except for there's some details about the interpretation that you have to be careful about. And it's like, for example, we'll talk about residuals. They will be plus or minus around the mean, which will be 0. Okay, but in RTOs, the mean of the residuals may not be 0. Okay, and then also we'll talk about what's called the coefficient of determination, and in RTO, the R-squared is calculated differently from regular regression, so you can't compare the models. Okay, so we won't talk anymore about RTOs. That's just sort of a heads up that if you do that, it's perfectly fine, but the interpretation is going to be a little different. Okay, so I've already mentioned some qualities about the regression, and that's you're going to have your fitted line, and then you can talk about the differences between prediction, which is what the line's all about, and the observations, and those are called residuals. Okay, since it's an estimate, you can come up with a confidence interval for the regression, and so I've drawn that over here, and this would be the idea then is that here's our prediction line, here's our original points, and the shape of the confidence interval is going to be, well, it's not flat, right? It's going to be narrow in the middle, and it increases as you get further away from the middle, all right? So what this has as a consequence then is that, the whole point to build a model is so that you can make predictions about unobserved. You get a new observation, and so you want to predict where will be the y value. So you use your regression to make the prediction. And as long as you're within the range of the data points that you made the model, you have some confidence that the prediction will be 95% or better, right? But once you get outside the range for which the model was constructed, you have less confidence in the predicted value, and that's because the shape of the confidence interval increases outside the range. Okay, so this is just a reminder that we're talking about a particular class of models called general linear models, and we've been introduced to them throughout the course. The t-tests and the ANOVAs were all general linear models, and certainly simple linear regression, multiple regression, these are examples of the general linear model. There's another one called the generalized linear model, and I don't talk about that, but that's a different kind of thing. Here are the components of the general. Okay, the variables can be quantitative. Okay, the response variable, I should say, and that's the difference with the GLN. The general linear model will handle when the response variable is categorical. Okay. But anyway, getting back to the general linear model, we assume that the response variable is normally distributed. Then the predictor variables can be quantitative or qualitative. Okay, or they can be a mixture of those. We can have different predictors, and some of them are qualitative and some of them are quantitative. Okay. Since we can have quantitative, that means we can build in our ANOVA designs. Factors are nested or crossed. The design is balanced or not, replicated or not. So the general linear model is just that. It can handle far more situations that you're likely to need to design and analyze experiments. Okay, so quick example, introduced back in chapter 4 some data where we had used teas, different teas that were purported to have antioxidant capabilities, and so we fed our cells combination of yeast extracts with and without copper. Copper is a metal that will generate reactive oxygen species. Reactive oxygen species damage DNA, so the idea was that we would measure DNA damage in our cells exposed to copper, and then in the presence of Ts or no Ts, with the idea that if Ts are antioxidants, then we should see reduced DNA damage. Reduced DNA damage would mean shorter tails in our comet assay. So these are two comets, and you can't really see it, but the tails extend out here, indicating DNA has been broken up and has migrated in our electrophoresis gel, and we took pictures, and then we measure the lengths of the tails, right? Okay, so we've analyzed that in various ways throughout the semester. We're going to now analyze it using the general linear model. So Archimander, statistics, fit models, linear model, that'll generate most of our output. Then we also want to generate a nice ANOVA table, and so these are the R-Commander commands for that. So we're just going to scan through those fairly quickly. So here's our menu, right? Statistics, fit models, linear model. All right. If you were to write the command at the R prompt, it's just simply LM and then the parentheses, and then you build the model inside that. So R Commander gives you what looks like a very complicated menu box, but it's actually it's not too bad. So R Commander will just generate an object for you automatically, or you could enter the model name yourself. We're going to be using the comment tail, that's our response variable. And so we would click on that, and it would then, where's my cursor, it would show up here. Okay, and then the only thing that's in this is the T's, the different treatment factors. So we would click on that, and that would show in that box there. And we wouldn't have to do anything else. We just go ahead and hit OK. And this would be the result. And this should look familiar. This is just basically what we would see as in an ANOVA. But now what we have is, where's my cursor? There it is. We have basically our post hoc test. We're looking at, there were 3 different levels of the treatment. And so we'll end up getting 2 coefficients that we estimate the difference between copper and, the difference between one of the T's and T's with copper and hazel, and then the other one was just with hazel. Okay, so we end up seeing here that there was a slight difference, and I do mean slight difference. Okay. All right, so we want to just get an ANOVA table. This is a pretty complicated looking thing. Many of the parts have to do with if you are building a model where you want to estimate the autocorrelation features of or different error structures in the data. Okay, you could use that through here. Most times you just say, if you don't know what you're doing, go ahead and hit the defaults. Chances are those are good choices, and in this case it is. All right. This just explains what these are. This has to do with how you interpret and ask for specific calculations. Take the default. The default is type 2. Okay, so here's our ANOVA table again. Should look more familiar, right? Okay, so we're going to stop there, and we'll pick up on the next time with assumptions of linear regression.